Today we are going to discuss about memory management. Memory management is one of the core operating system services that any operating system has to provide. Let's first understand what is memory. Physical memory can be seen as a contiguous series of bytes which can be referenced by an address. And when you load a program, that program resides in that memory so that CPU can load and store data from that memory and can store the code that it executes in that memory. Now, in a multi-programming environment, we need to store multiple programs at the memory at the same time. So let's see what kind of challenges we have in order to do that. Let's first start with a very primitive model. Let's say we have some 1 MB of memory, and all the programs that we want to load and run at the same time are stored in a predefined location. So in this picture we can see that operating system is running from 4 KB to 5 KB address location, and we have shell, GCC, VI, Firefox running at different memory locations. What is wrong with this model? There are several problems we can see in this model. For example, I'm editing a file in VI, and I started with editing a file which is 1 byte long. Now the file grows bigger as I add more data. Now VI editor has a predefined location. It cannot go beyond the amount of memory that is given to VI. That's a problem. Second problem is memory protection. Firefox, if some malicious program is running and it wants to write to some address 0x4050, then it can potentially corrupt the operating system code and all kind of bad things can happen in the system. We don't want that. Protection is the second problem. Is there any other problem? Yeah. All the programs has to know which address location it has to run. For example, VI editor uses a function to go to certain address based on some condition. So it has to know that which is the exact location in order to fit into this model. So from all this argument, we can say that this model is not very primitive model, and we want a better model than this. In our first attempt to improve the primitive memory management scheme, what we will try is load time linking. What we can do now is we can change the reference pointers when we are loading the program. For example, we are running a program a.out. A.out has this instruction jump at 0x1500 address at some point. We know the memory location required for a.out is 2000 bytes, and it wants to jump to the instruction at 1500 byte, 1500 address. So when we load a.out, what we can do is we can load to a available memory location and we can modify all the references it has got. So this scheme is called load time linking. Now let's see if this method is going to solve all our problems or if it still has some issues. It does not solve the problem of protection because a.out can go to any addresses for that matter. Instead of jumping to 0x1500, we could have jumped to some other address which doesn't belong to this limit. We can solve this problem with little improvement over the load time linking. Let's see what is that. So one improvement that we can do on top of the basic load and linking schema, we can do a base and bound register approach. What is that? What we can have is we can have two registers, and one will store the base for the base address for that program that we are going to run, and a bound register which will store how long is the program. So whenever operating system loads a new program, it can load these two registers with these two values for every program. Whenever any reference for that program is trying to cross that bound, it can cause a fault, and that will cause the program to terminate or any other thing that we may choose. By doing that, we will achieve the protection part of the memory management. So any program running in the operating system in the memory layout now has to be bound by the given address space by the operating system. Now it solves the protection problem, but does it solve any other problem? We also solved the predefined address space issue. Now the address references are going to get modified during the load time, but we still have not solved the problem that the program may expand during runtime, or it may require more memory address. So those problems we still have to solve. So let's look for other mechanism that we can improve, other mechanism that we can use to improve over our current scheme. Before we go to the next scheme, let's understand few definitions. So we are already talking about local address space and actual physical memory address. So the way the program knows about the memory address, that is called logical address, which may not be the actual address when it is placed into the physical memory. And the physical address space is the actual address which represented a address in the physical memory space. Generally, we have some kind of memory management unit which does the translation. We'll go in more detail how the translation happens. But before that, let's understand there is one more issue that we haven't talked about, that is reusing memory address space. For example, we are running Firefox. If there are two different instances of Firefox, then we don't want to run the same program in two different memory locations. That will be wastage of memory space, because the code segment, that is pretty much read-only unit, and that can be only in one place in the physical memory, and all the instances of Firefox can really read the code from the same location. So how do we solve these problems? We'll see in the next scheme. Our next memory scheme is segmentation. Segmentation will solve many of these problems that we have discussed earlier. Let's say user has a virtual address 3128. A portion of the address can represent an entry in a segment table. What is a segment table? A segment table is nothing but what we have already discussed. It's a base and bound register. It's a table which maintains a base address and the length of the memory location that is allocated, and it also has a protection bit which tells whether this memory location is read-only or it's modifiable. Now every virtual address can be split into two part. One part, the most significant byte part, can point to an entry to the segmentation table, which will point to an entry which will give us a base address and the length. And the second part of the memory address will give us the offset that we are pointing to. So if the offset is bigger than the length specified by that segment, then it will cause a fault. That will take care of the protection part of the requirement that we have. If the offset is well within the length, then we'll add the offset to the base address. In this case, for 3128, the base address is 1000. So the new memory address that we get is 1128. and that will give us an address in the physical memory. So what is the advantage of having this segmentation table? Segmentation table solves several problems. One problem it is solving is the protection that we are already solving using the base and bound register scheme. Another problem that it is solving is, if I told you earlier that if there are 5 instances of Firefox running, then we don't want to load the same Firefox program 5 different times. Now we can split the program in different segments: code segment, data segment, stack, heap, and all this part can go into a different physical address location. The code segment doesn't have to be loaded every time we load the new instance of the program. Uh, the address can point to the same segmentable entry for different instances, and it can have its own data segment, stack segment, which can carry different data and stack information. Now, segmentation pretty much solves a lot of the problem that we have discussed earlier, but it also has some inherent problem. The problem with segmentation is, um, once we start loading different programs, every time a new program is loaded, it uh, it defines an arbitrary space in the physical memory. Now, what can happen by doing that is, for example, one program asks for 400 uh, bytes of memory, another program comes and asks for another 400 bytes of memory. Now, and the third program comes and asks for another 400 bytes of memory. Let's see in this picture. 400, 400, 400. And we have more space here, more space here. Now, for example, 400, 400, 400. Now, this program terminates. So this 400 bytes of memory is now available for other usage. But another program which may join, that may have a requirement of 600 bytes. So going forward, if we allocate in this scheme, then we'll see that the whole memory is getting fragmented in smaller byte size, and at one point we'll come into a scenario where, though we have a huge memory space available, the whole memory space will be fragmented, and we cannot give a contiguous memory as requested by a program, and programs will fail to load. So this kind of fragmentation is called external fragmentation. The biggest problem that we have with segmentation is external fragmentation. Let's see how we can solve this problem with another scheme. The next scheme to solve the problem we discussed earlier is paging. Paging is very similar to segmentation, but in paging we divide the entire physical memory into fixed sized chunks. For example, in this example I'm showing that I've divided the entire memory in 100 bytes chunk. So when a program asks for some memory allocation, for example 100 bytes, we can give one page of memory. If it asks for 50 bytes, we still give 100 bytes of memory, and if it asks for 200 bytes of memory, then we give 2 pages. So what is problem with that? And how does it solve the fragmentation problem? So every time, since we are giving only memory unit in terms of 100 bytes, so when the program goes away, it frees up 100 bytes of the same fixed chunk of memory. And if another program asks for any arbitrary amount of memory, we can give the same amount of memory available from different locations in the physical memory. So it seems to be fixing the external fragmentation problem. But does it have any other problem? Paging has a different type of fragmentation problem, which is called internal fragmentation. If a program is asking for 1 byte of data, now we cannot give 1 byte of data. We have to give 100 bytes of data. 100. We cannot give 1 byte of memory. So we have to give 100 bytes of memory. So that means 99 bytes are getting unutilized. So that is called internal fragmentation. Paging has this problem of internal fragmentation. And the other problem that paging has is we have to come up with a page size. If the page size is too small, then we will have too many page table entries, and that will become a problem. Maintaining such a huge page table, we have to load the page table every time. That becomes a problem. If we have too big a page size, then we'll have a big amount of internal fragmentation. So with paging, one thing that we have to very carefully choose is what should be an ideal page size. We'll see in few minutes that how we can use this paging and segmentation together to get to find out an optimized scheme which can work in most practical scenarios, and it can solve most of our memory management problems. By joining these two schemes, paging and segmentation, we can have a schema where we can use best of both of these things. So the program, any program, when it's loaded in the memory, it has different segments which are text, data, heap, stack. So we can have a segmentation table which will enforce the protection bit. So for example, if it is a text segment, then we don't expect that code to be modified in the runtime. So that should be read-only. Whereas stack is always modifiable, so it will be read and write. So all these segments will point to a entry in the segmentation table. From segmentation table, it will point to a page table, and in page table we can have entries for different page index and the offset. Based on the page entry, we can go to that physical address page, physical page, and from the offset we can go to the actual memory location. We can take a example and see how this will actually work. So let's take an example of memory paging plus segmentation scheme, where we have a 16 bits address space, which is 64 KB address space, and we can have the scheme as 4 bits of segmentation table entry number. 4 bits are used for page table number, and 12 bits for offset. So from 12-bit offset, we can tell that the page size is 2 to the power 12 entries, so that means it is 4 KB page size. Now if user gives an address of 0x12226AB, the first 4 bits, it indicates a segmentation number. The seg number here will take us to the segmentation table, and from there we can find the corresponding page table and also get the protection bit, whether it is readable or writable. And in the page table, the entry 22, the page table number 22, will give us a base address in the physical memory, and the offset 6AB will give us the actual location in the physical memory. So this way we can utilize the base part of the segmentation table, the page table, and we can manage the memory in the most efficient way, which will solve most of the problems that we have discussed earlier. With this, I will end the memory management scheme. In the next session, I will discuss virtual memory, where we will see that um, how we can extend this scheme to swap the address, swap the memory location between hard disk and memory, and without having actual um, memory, how we can utilize um, a bigger address space. With this, I want to end this session. See you in the next session. Bye.